Welcome you all. Today we are going to discuss one more problem in a gas turbine. In a compound gas turbine, the air from the compressors passes through the heat exchanger heated by the exhaust gases from the low pressure turbine and then into the high pressure combustion chamber. The high pressure turbine derives the compressor only. The exhaust from the high pressure turbine passes through the low pressure combustion chamber to the low pressure turbine, which is coupled to the external load. The following data refer to the plant. Compression ratio in the compressor 4, isentropic efficiency of the compressor 0.86, isentropic efficiency of high pressure turbine 0.84, isentropic efficiency of low pressure turbine 0.80, mechanical efficiency of drive to compressor 0.92, heat exchanger effectiveness 70%, temperature of gases entering high pressure turbine 660 degrees centigrade, temperature of gases entering low pressure turbine 625 degrees, Cp and gamma for air is 1.005 kJ per kg Kelvin and 1.4, Cp and gamma for gases 1.15 kJ per kg Kelvin and 1.33. Ambient conditions are 1 bar 15 degrees centigrade. Determine A, the pressure of gases entering the low pressure turbine, B, net specific, C, the overall efficiency. First we have to write the given data. The air from the compressor passes through the heat exchanger heated by the exhaust gases from the low pressure turbine, then to the high pressure combustion chamber, then expanded in high pressure turbine, then low pressure compression chamber, then expanded in the low pressure turbine. Now they given that initial pressure and the temperature are 1 bar and 15 degrees centigrade. The pressure ratio in the compressor is P2 by P1 is equal to 4. Then isentropic efficiency of the compressor 0.86. Then isentropic efficiency of high pressure turbine is equal to 0.84. Low pressure turbine 0.8. Mechanical efficiency of the compressor 0.92. Effectiveness of heat exchanger 70%. Temperature of gases entering high pressure turbine T4 is equal to 660 degrees centigrade, that is equal to 933 Kelvin. Then temperature of gases entering low pressure turbine 625 degrees centigrade, T6 is equal to 625 degrees centigrade, that is equal to 898 Kelvin, and the Cp of Kelvin, gamma of air is equal to 1.4, Cp of gases is equal to 1.15 kilojoule per kg, gamma of gas equal to 1.333. Now with this given data we have to make a TS or HS diagram, in this case TS diagram. Now this process 1 to 2 is a compressor and 2 dash to 3 dash is heat exchanger and 3 to 4 is the combustion chamber 1, then 4 to 5 is the high pressure turbine, then 6 to 7 dash is the low pressure turbine, then 7 dash to 8 is the heat exchanger. The temperature entering the turbine is 288 Kelvin and 1 bar. Then the pressure ratio in the compressor is equal to 4, means this one is 4 bar. Then the temperature entering high pressure turbine is 933 Kelvin. Temperature entering the low pressure turbine is 898 Kelvin. Then the effectiveness of heat exchanger they given. Now find the pressure of gases entering low pressure turbine, that is equal to P6 or P5. Then the net specific power, then overall efficiency of the cycle. Solution: in compressor, isentropic relations T2 by T1 is equal to P2 by P1 whole to the power gamma minus 1 by gamma. T2 is equal to T1 into P2 by P1 whole to the power gamma minus 1 by gamma, that is equal to 288 multiplied by 4 whole to the power 0.4 divided by 1.4. T2 is equal to 428 Kelvin. Now we know that isentropic efficiency of the compressor is equal to T2 minus T1 over T2 dash minus T1, that is ideal compression over actual compression, that is equal to 428 minus 288 over T2 dash minus 288. Efficiency of the compressor is equal to 0.86. Then T2 dash is equal to 450.8 Kelvin. Now work of compressor per kg of air is equal to Cp of air into T2 dash minus T1, that is equal to 1.005 multiplied by 450.8 minus 288, that is equal to 163.6 kilojoule per kg of air. Now this work of high pressure turbine multiplied by mechanical efficiency is equal to work of compressor. Then work of high pressure turbine is equal to work of compressor over mechanical efficiency. That is equal to 163.6 over 0.92. We get 177.8 kilojoule per kg of gases. Now this work of high pressure turbine is equal to Cp of gases multiplied by T4 minus T5 dash. That is equal to 177.8 is equal to 1.15 multiplied by 933 minus T5 dash. That is T5 dash is equal to 778.4 Kelvin. Now we know that isentropic efficiency of high pressure turbine is equal to actual expansion over ideal expansion T4 minus T5 dash over T4 minus T5. Isentropic efficiency of high pressure turbine 0.84 is equal to 933 minus 778.4 over 933 minus T5. We get T5 is equal to 749 Kelvin. Now we know that isentropic relation of high pressure turbine T4 over T5 is equal to P4 over P5 whole to the power gamma minus 1 by gamma. Then P4 by P5 is equal to T4 by T5 whole to the power gamma by gamma minus 1. 4 over P5 is equal to 933 over 749 whole to the power 1.333 over 1.333 minus 1. P5 is equal to 1.66 bar, that is equal to P6. Answer the pressure entering the low pressure turbine. The second question is net power. So work of low pressure turbine is a net power output, that is equal to Cp of gas into T6 minus T7 dash. We know T6, we don't know T7 dash. But the isentropic relation of low pressure turbine, we know that P6 over T7 is equal to P6 over P7 whole to the power gamma minus 1 by gamma. Then P6 is 898 over T7 is equal to 1.66 over 1 to the power 1.33 minus 1 divided by 1.333. Then T7 is equal to 791.8 Kelvin. We know that isentropic efficiency of low pressure turbine is equal to T6 minus T7 dash over T6 minus T7. That is equal to 0.8 is equal to 898 minus T7 dash over 898 minus 791.8. T7 dash is equal to 813 Kelvin. Therefore, work of low pressure turbine is equal to Cp of gas 1.15 multiplied by 898 minus 813, that is equal to 97.75 kilojoule per kg. Power output is equal to 97.75 multiplied by kilowatt over kg per second. The third one is efficiency of the cycle is equal to net work done over the heat supplied, that is equal to work of low pressure turbine over the heat supplied is 2, that is heat supplied at the combustion chamber 1 plus heat supplied at the combustion chamber 2, that is Cpg into T4 minus T3 plus Cp of gas into T6 minus T5 dash. So here T3 is the unknown term, T4 we know, T6 we know, T5 dash we know. We know that effectiveness of heat exchanger is equal to actual heat transfer over maximum possible heat transfer. The actual heat transfer is H3 minus H2 dash over H7 dash minus H2 dash per kg of air. Cp of air multiplied by T3 minus T2 dash, then Cp of gas T7 dash minus T2 dash. We know that effectiveness of heat exchanger is equal to 70%, that is 0.7 is equal to Cp of air 1.005 T3 minus T2 dash 450.8 over 1.15 multiplied by 813 minus 450.8, we get T3 is equal to 740.6 Kelvin. So that heat supplied is equal to Cp of gas into T4 minus T3 plus Cp of gas into T6 minus T5 dash. That is 1.15 multiplied by 933 minus 740.6 plus 898 minus 778.4. We get heat supplied is equal to 358.8 kilojoule per kg. Then cycle efficiency is equal to net work over heat supplied, that is equal to 97.75 over 358.8 is equal to 0.2542, that is equal to 25.442% answer. The answers are: pressure entering to the low pressure turbine is equal to 1.66 bar, and then B, the specific power output is equal to 97.75 kilowatt per kg per second, and third, overall cycle efficiency is equal to 25.42%.
Subscribe to our channel, like if you're satisfied, and share because it may be useful to someone.